Okay, gang, welcome to CSC 475, Artificial Intelligence. Today, we're going to be talking about continuing our talk about good old-fashioned AI, where we're talking about game playing. Specifically, we're going to be talking about search today. If you'll remember from last time's lecture, we talked about state space, which is a way of modeling some kind of an environment, usually a game, but you could model more complex environments. And basically, you have a state, some compact representation of the current state of a problem or a game or something like that. So if it's a game board, the state would be kind of a two-dimensional array that had some indication of what all the game pieces are and also whose turn it is. So you have to have that. You have to have information about how you move between states. So what are the rules of the game? And then you have to have some way of recognizing a win, and conversely, sometimes ways of recognizing losses as well. So that's a state space representation. And then if you've got that, you can use search to kind of look ahead to various possibilities and use that knowledge of the future by kind of playing out various scenarios to figure out the best move to actually make. There's a movie, oh gosh, and I'm going to forget, I don't remember the name of the movie, and I'm going to forget the actor's name too. He's been in everything. Raising Arizona is my favorite movie that the guy was in. Help me out here. Somebody in chat. Anybody remember Raising Arizona? Nicolas Cage. Right, Nick Cage. And there's a movie from about, 10 years ago maybe. And it's about this guy that, can avoid bullets and can do all of this sort of stuff. And you're kind of like, well, how is he able to do this? And then when you get towards the climax of the movie, there's this big scene, but they show you how he does it, which is basically he searches out every different strategy, right? And so it shows, him playing out one path and getting killed there, and then going down another path, and going down another path. And then basically he plays out all these scenarios in his head. He looks through all of them. And then, of course, he can make the right move because he's searched through all of the possibilities. Well, that's essentially what we do in AI, all right? We play out all of the different ways the game could go, and then we take our best shot. Now, the problem is that any kind of reasonably complex game, there are going to be too many options for you to play them all out. You don't have enough memory and you don't have enough time. So that's why the simple methods of depth-first search and breadth-first search that we talked about have limitations. They're okay for small problems, but if you get to a larger problem, you run into issues because you just don't have enough time and space. So that led to the development of what are called heuristic searches. Depth-first search and breadth-first search are called blind searches because you're basically blindly looking through the space of possibilities. But with heuristic search, you use a heuristic. You use an estimate, some kind of a way of judging how good a problem state is. And so we looked at hill climbing, which was a very simple heuristic search. And basically that search just says, okay, I'm at some position. Look at all of the positions directly adjacent to me. And if any of those positions is better than, as judged by the heuristic, then the current state that I'm in, move to it and repeat. And And it's called hill climbing because if you think about it, you're trying to move upwards to reach the maximum altitude, right? The maximum position, the highest point. And you take the next step that seems to be the highest of all of the steps that are available next to you. Now, hill climbing, of course, is simple, but it runs into a lot of problems. The biggest one is it gets stuck at local maxima. So what happens when you're standing in a position and every next step seems to go downhill rather than uphill? Well, then you get stuck with hill climbing. Hill climbing, I think I ended up last time saying that hill climbing, you can think of it as you're trying to climb a hill or through a set of hills to get to the top of the highest mountain or the highest hill, but you're doing it in fog, so you can't see very far, and also you have no memory. You're amnesic, so you don't know how you got to where you're at. All you know is you can look around you, and whatever looks best, you take that step. Okay. Now today, we're going to talk about two different algorithms that dramatically improve on what you can do with hill climbing. The first algorithm, classic algorithm, is called A-star. A-star is an algorithm that searches a tree or a graph, and it has a heuristic like hill climbing does, but it also has a memory. It knows how much it costs to reach a particular spot, okay? And using both of those components, how much it costs to reach a particular node, and then how much we think it's going to cost from this node to reach a goal. So the heuristic tells you from this node, I think it's going to be 10 steps to reach the goal. So that's an estimate. But you also have the, oh, I've already spent 5, I'm going to have to walk 5 paces to get to this node. Well, those two things together, how much it actually costs to get to the node, plus how long you think it'll take you from that goal to reach, from that node to reach the goal, those two things together give you an estimate of the total cost of reaching the goal through that node. And what A-star does is it's a best first search. It looks at the best possibility, and at any point in time, it always explores what is currently the best estimate, the best possibility. So A-star is a best first search. So you've heard of breadth first search, right? Where you do all of the children at one level before you go to the next level. And you've heard about depth first search, which is you go all the way down right before you back up, right, when you hit dead ends. Well, A-star is best first search. You look at the best path first. Now, A-star is a great algorithm. It's a classic algorithm. It is for single-person games. So finding your way through a maze is the classic example that's given there. Or the farmer wolf goat cabbage problem. Very small search space there, but it's the kind of problem that you would use A-star to solve. Farmer wolf goat cabbage is so small, there are only 16 states. You could use depth first or breadth first to solve that one. But if you have a similar kind of problem, but with more choices to it, more steps, then A-star becomes practical. So A-star is for single player games. The next thing after A-star that we're going to look at today is called Minimax. Minimax is the classic algorithm for a two-player game, a two-player zero-sum game. That is a two-player zero-sum game is a game that's played between two people, and one person wins and the other person loses, or vice versa. So it's called zero-sum because if you take the win, count that as a as a 1 and a loss as a -1, well, if you add up the win and the loss, it's a zero sum. So one person has to lose and one person has to win. Of course, you could tie when they both get 0, but it's a zero sum game. So we'll talk about Minimax, and then once we become comfortable with how Minimax works, we will then talk about an enhancement that you can do to Minimax called alpha-beta pruning. And alpha-beta pruning is simply a way of, it doesn't change the output of the algorithm, but it provides a way that you can sometimes skip doing work if you can figure out that that work is useless, that work wouldn't change the final answer no matter what. And so that's what alpha-beta pruning is. So that's what we're doing today. So let's start off looking at A star. Let me see, I need to share my screen here. Okay. So again, I've said that A star is the best first search. It really combines advantages of depth first and breadth first search together into a heuristic search. So a lot of times what you'll do is you'll explore a path for a while in kind of a depth first manner, and then when that path no longer looks so enticing, a lot of times things look good, and then you start going down, exploring a little further, and the more you learn about it, the less good it looks. So it's kind of the same way. You'll depth first explore a little bit, but frequently what will happen is after a while, what looked real promising, you start seeing, no, it's going to cost more than I thought it would, and then you switch and you go over to the next best looking option. So you kind of go depth for a while, and then you branch out to go breadth for a while. And so it balances those, the depth first tendency and the breadth first tendency. It balances them by always looking at the currently best option that you have. So at each step, A star selects the most promising of the nodes that have been generated so far. Here is the basic equation that you have. F prime of n, which is an estimate, the little prime there means it's an estimate, is a combination of g of n plus h prime of n. H prime of n is our heuristic function. The little prime there is because it's an estimate. You don't really know the cost of reaching the goal from node n. When I say h prime of n, I mean the cost of reaching the goal from node n. It's an estimate. I don't have perfect vision. If I had perfect knowledge, I wouldn't need to be doing the stupid search. I would just walk directly to the goal. So I don't have perfect knowledge of how much it's going to cost in the future to reach the goal. I should have perfect knowledge of how much I need to spend to get to node n. So that's what the G of n is. It's how many steps you've taken or how much you've spent to get to node n, plus how much I think I'm going to have to spend to reach the goal from node n. Add those two things together, and that gives you an estimate of what I think it will cost to reach a goal through node n. Okay? Does that make sense? Okay. So if we look at a little graph here, this is a graph where we're using uniform cost. Now, what does uniform cost mean? Uniform cost means that each choice that you can make is assumed to take the same amount of effort. And in a lot of things, that's true. But in other things, it isn't. If if all of the nodes represented cities, for example, and the arcs represented roadways between those cities, well, going from Ruston to Shreveport, I could go from Ruston to Alexandria, or I could go from Ruston to Monroe, the three largest cities that are nearest to us. But the cost in time or in miles or in gas, or if you've got an electric car and charge capacity, of going from Ruston to Shreveport is different than that's like what? That's an hour, say, right? But the cost of going from Ruston to Monroe is like 30 minutes. All right, in Alexandria, it's like, I don't know, what, an hour and a half or something to go to Alexandria, 2 hours? I'm not sure. Haven't been there in a while. But the point I'm trying to make is sometimes it's every move costs the same. In other situations, different moves have different costs associated with them. In this particular problem, we're saying that all edges cost the same. Usually we use a 1. You'd get the same number if we said the cost was a 5 for all of the nodes. For each node was a 5, or the cost was for each node was for each arc was a 10. But usually we just say 1, right? The heuristic that we've got here is going to be a non-admissible heuristic. Now, remember what we talked about last time about heuristics. There are 2 types. There are admissible heuristics and non-admissible heuristics. An admissible heuristic is a heuristic that when it has an error, it errors by being overly optimistic. If I'm going to be wrong in any direction, an admissible heuristic is wrong in being overly optimistic. It thinks that the goal is closer than it is if it has an error. So it errs on the side of being optimistic, right? A non-admissible heuristic is one that can overestimate the cost to a goal. It can be overly pessimistic. So in this case, if we go and we look at this graph, we will see that it is a non-admissible heuristic, because if we look at node D and we look at node I, node D thinks that it will take you 5 steps to reach the goal from D. Well, since we can see the whole graph here, now remember the algorithm doesn't see the whole space. It starts at A, and when it's at A, all it knows is A, and then it can look and find and see B, C, and D, right? But it doesn't know any of this other stuff to start with. So that's why you have the heuristic. The heuristic says, I think it's going to cost me thus and such to reach the goal. So D is pessimistic. It thinks it's going to be 5 steps when it's only 2. And I is also pessimistic. It thinks it's going to be 3 steps when it's only 1. So in node D and in node I, you're overestimating the cost of reaching the goal. When you do that, that can cause A star to overlook a better path. So let's step back and let's walk through this very slowly, very carefully. So I'm at A, and the first thing I need to do is I need to open up to explore my children. Let's see my children. I see that I've got a B, a C, and a D. And when you open that child, you compute its heuristic. Okay, I go to B, and I think that, oh, I can reach a goal in only 1 step from B. That's what this H prime of 1 means. And then I look at C, and I said, oh, it's going to take me 3 steps, I think, to reach the goal from C. And, oh, I think it's going to take me 5 steps to reach the goal from D. Now, where do these numbers come from? I'm pulling them out of the air for this example. There is no heuristic function in this case. I'm just making up these numbers. But you you might think, well, you know, this guy's accurate, you know, and you might say, well, you know, he thinks it's going to be 3 steps, and looking ahead, which the computer cannot do right at this point, but we have a bird's eye view of the whole thing. I think, see, there really is 3 steps. But you also note that after C, there are no choices, right? It's just boom, 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 boom. C has 2 choices, right? D and G, but G only has 1 choice, J, and J only has 1 choice, M. So maybe the heuristic function is more accurate here because of the way the search space is set up. It's a fairly clear path from C to M. There are not a lot of choices, right? Again, I made up, you know, these numbers 1, 3, and 5 here. I'm just trying to say, well, why might a heuristic function generate a number like this? Why might these numbers have some sanity behind them? Well, what about D having 5? Well, you see that D has choices, but it also has a bunch of failures in it forward. So maybe the fact that there are ways that you can fail in the future somehow influence the heuristic function. So it's like, oh, that looks kind of scary. That's 5. And over here, 1, well, I don't know. It's harder for me to make up a reason why this one might be 1. It's got a failure in it, but, you know, then it's got an F here. So I'm pulling this one just out of my back pocket, right? So again, you would have a heuristic function that would somehow, I'm not showing you how here, would compute these numbers, where these numbers are a representation of how long, how many steps the algorithm thinks that you will take to reach the goal. From D, I think it's going to be 5. From C, I think it's going to be 3. From B, I think it's going to be 1. Now, that's not the total cost of getting to the goal, say, from A, going through C is not 3. The total cost estimated of getting to the goal through C is 4, because it's the 3 from the heuristic, right? Plus it took us 1 step to get to C. So that's why you see these F values are 1 more than the H values here. So yeah, I think it's going to take me 5 steps to reach the goal from D, but it took me 1 step to get to D in the first place. So I think it's going to take me 6 total. So okay, so at this point, all I know is that A has 3 children, B, C, and D, and I think the total cost of reaching a goal through B is 2. The total cost of reaching the goal through C is 4, and the total cost of reaching the goal through D is 6. And then, since A star is best first, it sorts these things by, it basically uses a priority queue, where it says, okay, I'm going to sort these from best to worst. And in fact, in this case, they happen to be left to right, sorted from best to worst, right? So the next node that I explore is B. So B, essentially at this point, I'm exploring the path from A to B. So now I repeat the same thing. I say, okay, what are B's children? Well, B has children E and F, and then I apply the heuristic function to each of them. Well, E is a loss, so its cost, the number of steps to reach the goal from E, is infinite. You can't reach the goal from E because it's a dead end, so it has infinite cost. So F is also infinite. The full cost of reaching the goal through E is infinite. Why? Well, because infinity plus 2 is infinity. Okay. F says, okay, when I was at B, I thought I was really close to my goal. But when I see E as a dead end and F, it's not close to the goal, I reassess and I think, oh, F's far away. It's 10 steps from the goal according to the heuristic. So the total estimated cost of reaching the goal through F is 12, 10 from F and 2 to get to F. Now, you might say to yourself, but Mike, the cost of reaching the goal from F is not 10. That's true. The goal is not 10 steps away. In fact, you can see that really this is an infinite loop here, right? So if you just stick with that path, you'll never reach a goal. But the heuristics aren't perfect. They can't really completely see the future. Again, what's a heuristic? If I'm thinking about a maze, okay, a simple heuristic would be I look at the line of flight distance between where I am and where I know the exit of the maze is. So I don't know all the details about the maze. Got to add my background back. Can't be without my background. Gotta have our Westport there. I don't know. I don't know everything, but if I know approximately where the exit is, right, and I know where I'm at, I can, look at the straight line distance. And so at least I know whether I'm getting closer to the goal or further away from the goal. Now, the thing about mazes is a lot of times you'll get really close to the goal and then you'll have to move far away from it again, right? But if you don't have anything else, if you know at least, your distance from the goal, straight line distance, that is a heuristic that you could use to estimate whether you're getting warmer or colder at least. Okay, so now where are we? Well, we explored A's children, B, C, and D. We opened them up, and we decided since 2 was better than 4 or 6 to open up B. So now we can close B. So we closed A, we're closing B by exploring its 2 children. And we now see that we have E, F, C, and D are the possibilities. Well, if you order these from best to worst, C is better than D, is better than F, is better than E, because 4 is less than 6, is less than 12, is less than infinity. So of these 4 nodes, which is the best one? Clearly C is. So now then, I was going down the A-B path, so I took a step down there, but it didn't look nearly as good when I looked at its children. So now I'm going to look at AC. So I had started out in kind of going depth, but now then that this path isn't looking as good, I'm branching out to go more breadth first, right? Okay, so what do? Well, I open up my 2 children with C, right? That gives me G and D. I already have explored D and know its heuristic is 5. If I go to D by going A, C, D, the cost there would be 5 plus 2, which would be 7. But since that's more than the currently best known way of getting to D, I will ignore this branch. So if you rediscover a node that you've already discovered, and you rediscover it in a way that costs you more to get to that position, then clearly you don't want to go down that position. So you kind of you choose to forget about this link because it's not going to do you any good. It's not the best way of getting to D. The best way of getting to D is to go from A to D. Okay, but C has another kid. It has G, right? And G has a heuristic value of 2, but it took me 2 steps to get to G, so we've got a value of 4. So now at this point, I've closed A, I've closed B, I've closed C. My open nodes are E, F, G, and D. And G's got a 4, D's got a 6, F's got a 12, and E's got an infinity. Well, which one is best? 4, 6, 12, or infinity? Well, clearly the 4 is. So I explore G's children. There's only one of them. I open it up, and it thinks that it's just one step away from the. Did you guys lose my video? Yeah, y'all did.
Yeah.
Remember, if you don't have these notes in front of you, they are on Moodle, so that you can bring them up and continue to follow right along with what I'm doing here. Okay, so if you haven't already, you can go to Moodle right now, and you can pull up the lecture notes for 10/29/2020, and pull them right up. Okay, so I will assume that you have these notes in front of you, and I will just keep talking as if I'm showing them to you, even though I'm not. And when video comes back, we'll restore it. Okay. Okay. So again, at this point, we've closed A, B, C, and oh, did I come back? I think I may have. Can you guys see me again?
Yep.
That was a nope or a yep? Ah, yep. Okay. All righty. Because I am such an anal individual, I will bring back up my background one more time.
Dr. O'Neill, I have a question.
Cool. Yes, this is a good point for questions. Ask away.
So could you please repeat why f prime is one more than h prime in these paths?
Sure. 1 second, where I can pull up the okay. What is f prime? F prime is simply g plus h prime of n. Okay. What is g? G is the actual cost of reaching a node from the starting point. So when we're talking about the first level here, it costs me 1 to go from A to B. It costs me 1 to go to A to C. It costs me 1 to go to A to D. So if I think the cost of reaching the goal from B is 1, the total cost of reaching the goal by going from A through B is 2. Similarly, I think it's going to cost me 3 to get to the goal from C, but it's going to cost me 1 to get to C, so that's a total of 4. Notice when we go down to G here, right, F is not 1 more, F is 2 more than H. 2 plus 2 is 4. Why? Because it took me 2 steps to get to G, right? Plus 2 more steps, I think, to get to the goal. So I think the total cost is going to be 4. Okay? Similarly, when we get down here to J, I think I'm only 1 step away from the goal, but the total cost is 4 because there was 1, 2, 3, plus the 1 ahead of me that I think there is, gives me 4. Does that make sense?
Okay, thank you. Yeah, that makes sense. So green are the goals?
The green are the goals, yes.
Okay.
And reds are dead ends.
Okay, thank you.
So okay, at this point we've closed A, B, C, and G, and our open ones are E, F, J, H, and I. Well, actually, we haven't done H and I. We've done E, F, J, D. So 4, 6, 12, infinity, 4 is still smaller, right? So we would explore J's children, find that that's an M. Since it's a goal, the heuristic here is 0. It's not going to cost me any steps to get to the goal because guess what? I'm at a goal, right? But the F value is the G value of 1, 2, 3, 4 plus 0 is 4. So at this point, I have found a goal and it cost me 4. it was, given the heuristics that I had, the best path given the heuristics. Now, because the heuristics that I was using were non-admissible at D and I actually ended up overlooking a better path. A, D, I, J only costs 3, right? But I never explored this branch of the tree because this guy was pessimistic. It said, oh, this is probably going to be bad. So the path I was on was always looking better than that 6 here. So because of that, I didn't explore it. Now let's say we had kept going here, right? You get a little deeper, right? Every time you go down a level, that's adding 1. Your F value is going up by 1 each time. Pretty soon, after 2 more steps, this path would again start looking better, right? Because every time you take a step, you are increasing your total cost, right? So after a while, you would stop going in this depth first direction, and you would go over to another path that looked better. But in this case, you never did that because this 5 was just wrong. Okay? Now, we can, here I just trace through exactly what I just talked my way through. So if you were not 100% clear on what I meant by nodes that have been opened or closed and all of that stuff, and the priority queue, all of the details are just written out here. I've already talked my way through them, okay? Now, next I want to try to give you a feel for how the G of n is working and the H prime of n is working. So we can play some little thought experiments, some little mental games here. And the first thing is the G of n should always be greater than or equal to 0 for all n. That should always be true. Why? Why should G of n always be greater than or equal to 0? Well, what is G of n? G of n is how much it costs you to get to a certain node. You might say, well, Mike, there's no G's written here. Well, this is uniform cost. So, you know, the G here is 2 because it's 2 steps away from the goal. The G here is 3 because it's 3 steps away from the goal. So you can figure out that it must have been 3 because the H was 1 and the F is 4. So the G was 3, 1, 2, 3 steps. Okay. The cost of reaching a node can never be less than 0. If you start at A, what's the cost of reaching A? 0, because you started there, right? But no node can cost you less. I mean, you don't get, you know, rewards for you don't get negative effort, you know, for going down a leap, down a path. So G will always be greater than or equal to 0 for any n, any node that occurs in our graph. Does that make sense? Questions about that? Okay. Now, if G is equal to n for all n, what would that mean? If G were equal to, if G of n were to be 0 for every node, what would that mean? Well, that would mean that our F would always be equal to whatever our heuristic gave us, right? Because we're saying G of n is always going to be 0. Remember, our formula here is F prime of n is equal to G of n plus H prime of n. So if G of n is always 0, then F of n is just H prime of n. So you basically, in this case, you have no memory of how much it costs you to reach that node, okay? So you're doing away with your memory when G of n is always equal to 0 for all n. In other words, you'll take any path to the goal. The cost of a move is 0. We don't care about the length of the return path in this case. All we care about is the heuristic cost in this case. So that's if G of n is always 0. Now, what we just showed above was G of n is equal to the depth of n for all n. So you could figure out what your G was by just looking at the depth of this node. This node's, is at a depth of 2, so its G is going to be 2. This one's at a depth of 3, so its G is going to be 3. This one's at a depth of 1, so its G is going to be 1. A is the root. It's at a depth of 0, so its G is going to be 0. So G of n equals depth of n. We're modeling uniform cost. All moves cost exactly the same, usually 1. So what we're interested in is the least cost path. In this case is going to be the shortest path. The shortest path. So if G of n is equal to depth of n, then A star is going to return the shortest path. That's what it's shooting for. Now, if G of n returns different positive numbers for different nodes, we can model the idea that different moves have different costs associated with them. In this case, we're trying to find the least cost path. And the least cost path is not always the shortest path, because if this link costs you 5, right, and all the rest of the links cost 1, well, this would be 5, 6, 7 is the true cost of getting to L. All of these are 1 except this one, it's a 5. Okay, so the cost of getting to L from A would be 7. Well, even though that's a shorter path, it's still not the least cost path, because this is a 5. If all of these are 1, it costs you 1, 2, 3, 4 to get to this node. So sometimes the shortest path is not the least cost path if the links themselves have different costs associated with them. Okay. So that's talking about G. Is there any questions about G, what it means? It's always got to be greater than or equal to 0 for any node n, because there's no such thing as negative effort in these things. The cost of reaching reaching a node, the lowest it can be is 0, which means that's where you started from. Okay. Now, if we're trying to understand A star, there's 2 components, right? There's the G and then there's the H prime. H prime is always going to be greater than or equal to 0 for all n. Now, why is that true? Well, if I'm at a goal, how much effort am I going to have to expend to reach the goal if I'm at it? 0, because I'm at it. So, but that's the lowest estimate that you can have of the cost of getting to the goal from your current state is 0. Most of the time, if you're not in a goal state, right? I'm not in a goal state. I'm in one of these gray states here, right? It's going to cost more than 0 to reach the goal, because you've got to take it. You're not in a goal state, so you've got to take at least 1 step, right? You might have to take a lot more than 1 step, but at least 1. So H prime of n, the heuristic, is always going to be greater than or equal to 0. Now, what will A star do if your H prime of n equals 1, and for all n, and G of n equals 0 for all n? Well, what does this say? This says that I have no memory of how much it costs me to get to node n. Okay, I think it's 0. And I think I'll think every node is 1 step away from the goal, unless I'm at a goal. So all non-goal nodes I will think are 1 step away from the goal. So this is as optimistic as you can get. And I have no memory of what things cost. Well, that's essentially a random search because I have no concept of cost to reach a node, and every step looks just as good as every other step. So I'm wandering around completely blind. Everything looks just as good as every other thing, and I'm wandering around with absolutely no memory. I have no memory of where I've been and how much I spent to get to the point that I'm at, and I'm really completely blind because everything looks like I'm almost at the goal, right? Everything looks equally far away from the goal. So I'm getting no input from the heuristic, and I'm getting no input from the actual cost. So I'm randomly wandering around is what happens with A star in that case. Does that make sense? You got no memory. How much it costs to reach node in, and you get and the heuristic is always a 1. Everything always looks as close as any other thing. All goals look equally close. Okay, so what about if our heuristic is still giving us a 1, so everything looks equally far away from the goal, but our G of n is depth of n, so uniform cost, and we remember how much it costs to get to a node. Well, then what happens? A star becomes breadth first search. Why does A star become breadth first search in this case? Well, it's pretty straightforward. I start out at A. All of my heuristics give me 1, 1, 1, 1, right? And I come here and I explore B, right? And because all of the heuristic functions would be 2, 2, 2. All the F's would be 2 because all the H's are 1. So they all look the same. So I just randomly choose the first child, right? If everything else is equal, we'll go left to right. Okay, now I open up its children. Well, this H is going to be 1, this H is going to be 1, but the F is going to be 2 here, and the F is going to be 2 here because the G's are depth. So it remembers, oh, it's 2 steps here. So this is the 2, this is the 2, this is a 1, and this is a 1. So what are you going to do? Well, I'm going to go now and explore C's children, D and G, right? G's got a 2 in it. D's still going to have a 1 because it got a 2 from this direction, but we already have a 1 from this direction. So 2, 2, 2, 1. Who are you going to look at next? D. So look at what we've done. We went A, B, A, C, A, D, right? And after you finish that, you've got E, F, G, H, and I, and they're all at 2. So, you know, you would go here, but you find out you're at a dead end. Right?
Hey, see what y'all got.
Your mic
You know, I'll
is
get 6 of these wings right here.
yeah, your mic is not muted, and I would like 6 wings as well, if you don't mind. Anybody else want food? Because somebody's in the
I'll take
drive-thru
some
line.
wings.
I wouldn't mind.
Yeah. Okay. So continuing, this is being recorded to YouTube, so that will last for posterity. This
Great,
order
thank you
of
so much.
wings. Could you please mute your mic? Clearly, we're not listening to me, so he's not muting his mic. But my point
I
is,
think you can mute him.
oh, can I? Maybe
Yeah, I
did.
think
Yeah,
if
if
you go
you-
to participants and right click, you can mute him.
Yeah.
Oh, hold on. Is this okay? Let's. I right clicked, but I don't see.
I think it's if you hover over whoever's unmuted. It'll have the option to mute or more.
Yeah. There's so many of you guys. Well, he seemed to have gotten his wings, so I guess we can leave it alone at this point. I think there was a mute all at one point in time. Anyway, can I have a Frosty? I want a Frosty too. Actually, the wings sound good. I was working all through lunch with you guys, so I didn't get to take a break. Anyway, let's continue. Let's continue. Okay. Let's go back to sharing my screen here. So back on topic, does everybody understand that if you are having your G of N be your depth of N, and all of your heuristic functions always return 1, that A star is going to degenerate into breadth first search? Now, that's not such a bad place to degenerate to. Clearly, you can only solve small problems with a breadth first search, but it will still find the shortest path, right? So it'll still return a path for you in that case, and it'll be the best path, as in the shortest path. So it won't overlook a solution. It's just going to use more resources in that case. Okay, so A star becomes breadth first search and returning the shortest path in this case. Now let's say that H prime is admissible. It never overestimates the cost, and G of N is the depth of N for all N, the uniform cost model. Then A star returns the shortest path, usually examining fewer nodes than a breadth first search would have. The better the heuristic, the fewer the nodes that will need to be searched. And I think I have an example of that coming up. Let's see. I think I do. Here, that's non-uniform. Okay. Again, we can do it on this one if this had not overestimated, right? If this had been 2 and this had been 1, so that they were accurate. Okay, or even if they're not accurate, if they don't overestimate, so that's overly optimistic. Well, in this case, right, this is what things would look like. And so this is now an admissible search. I'm not going to save this off, but now it's an admissible search. Nobody overestimates. In fact, D underestimates. But in this case, you'll see what will happen. Your choices are 2, 4, and 2. Here, let's say since this is on the left, we take it first. Well, then it's infinity 12, 4, 2. So 2, 4, 12, infinity. So then we would open D, right? So we tried A to B, and we looked at B's children, but things started looking bad. So now we switch over to D, right? And we open its 2 children, infinity and 3. Well, 3, 4, 12, and infinity. 3 is still best. We open up its 2 children. We find L. So in this case, the heuristic was admissible. It never overestimated. Yeah, it could be overly optimistic like it was here, but at least it never overestimated. And we ended up, we wasted some time going down this path here because this guy looked really good to us at first. So all we ended up doing was wasting a little search time. We still found the least cost path in this case, the shortest path when you got uniform cost and an admissible heuristic. Does that make sense? Okay. Finally, if, well, not finally, next, if H prime is admissible, it never overestimates the true cost of reaching the goal, and G of N models a non-uniform cost, then A star will return the least cost path while often examining fewer nodes. So if we look, here's an example of that. A non-uniform cost, admissible heuristic, and A star will return the lowest cost path. Okay, now, why are some of these things in red? The things that are in red are just what changed from the previous example. So now then, this link costs 2, this link costs 2, this link costs 2, this link costs 4. So when you're at A and you look at your children, this guy still has an F of 2, 1 step, cost of 1 here, plus a heuristic of 1. This guy costs 5 because the heuristic's still 3. It's not 4 anymore, it's 5 because this link costs you 2. 2 plus 3 is 5. This link here, the heuristic says, oh, it's going to be 4. And you might say, wait, 4, there's only 2 steps. Well, yeah, but the cost here, looking ahead, is 6. So 4 is still, it's not overestimating the cost. It's still admissible. So I estimate the cost of reaching the goal is 4, but this is 4 plus 1, so the F value is 5. Okay, so who do you take, 2 or 5 or 5? Well, you take 2, but then you see that's an infinity and a 12, so now you have 5, 5, infinity, and 12. Well, which of these 5s do you take? We'll just take left to right. We don't know ever how your algorithm's set up, but if we're going left to right, we'll take C next. Okay, I think it's going to cost me 5 to reach the goal through here. I look at its 2 children. D through AC would cost me 3 plus 4. That's 7. 7 is more than 5, so we ignore again this path here. You know, you wouldn't always ignore this path. Let's say this was a 5, right? Even though this path was longer, you might end up switching D's parent to be C in that case, because 2 plus 1 would be 3, and if this one were 5, you have actually found a longer but cheaper cost path to D. So don't think, oh, I'll always forget about this. It depends on the situation and whether you're uniform or non-uniform cost. But anyway, so I thought it was 5, so I opened its 2 children here, G and D. G's 2 steps away from the goal, so I think, but it cost me 3 to get there, so that's 5. So it's still 5, 5, 12, and infinity. But since these are both 5 and I was already going down this path, I'll go down it again. So now I get a 6 here because I think I'm 1 step away from the goal, but it cost me 2 plus 1 plus 2, so 5 plus 1 cost me 6. So I've gone all the way A, C, G, J, but I am now going to switch over to D because 5 is cheaper than 6, is cheaper than 12, is cheaper than infinity. So now then I go here, I explore its 2 children, infinity and 6, because I think it's 3 steps. I think it'll cost me 3 to get to L, and it cost me 3 to get here, so that's a total of 6. So now then you got a 6 here, an infinity, a 6, a 12, and an infinity. So we've got these 2, right? Now let's say, for the sake of argument, that we go back here to J and we open it up, right? And we see that we've got a goal at 6, but we're not really finished yet because the value here is 6 and the value here is 6. We really should explore this one because this H is just an estimate, right? We do that, and because the estimate could be wrong. We do that, and it does turn out that this is the cheapest path of 6 here, A, C, G, J, M. Okay? So we got our, we reached our goal with the least cost path. Okay. All right. Let's see. if there are questions at this point. This feels like Dijkstra's algorithm. Yeah, it's not too different from it's not the same as, but it's not too different from Dijkstra's algorithm. For those of you who had 325. And somehow I got my chat to pop out. That's useful. That's useful. Okay, there was one other case that we wanted to look at, right? If the H prime is inadmissible, it overestimates the cost of reaching the goal in some cases. A star will still find a path to a goal if one exists, but it's not guaranteed to find the optimal path. We've already seen that if you get a case where it's where your H is inadmissible, it could overlook a better path. So that's A star, right? I would like for you to try your hand at this one. So why don't each of you take a few moments and try to figure out what A star is going to do on this diagram here. Take a few moments and try to work through it. This is the typical kind of a problem that I would give you on an exam. So A star is only as good as the heuristic function. Yes, that's true. If your heuristic function is basically blind, it degenerates to breadth first search, as I showed you in the example. And the reason why I'm going through all those examples is I'm trying to give you a feel for how the algorithm works and the way G influences what it does and the way H prime influences what it does. And yeah, Christopher, graph theory concepts and algorithms are often used in symbolic AI. This is really 325. That's what this is. Sometimes you cover A star in 325. It's such a common algorithm, but it is an algorithm that's generally taught in AI. Okay, so grind through that. Let's see if you guys can figure out what it's doing and what path it'll end up returning. So I'll give you a few minutes. Okay, let's see what we came up with. So, first you start at A. That's the starting point, and there's nothing that you've closed. Your open list, those are the children, right? Consist of C, D, B, and E, and I give their F values there, right? So C is 5 because the heuristic is 2 and the cost of reaching it's 3, right? The next best is D because it's 3 plus, sorry, it's not 3 plus. It's 5 plus 3, which is 8, right? And then B is 10 plus 15 or 25. and E is 10 plus 30 or 40. So C looks like it's going to be best. So that's what we have. So C is chosen. A is now closed. So on C, you now explore C's children, I and J. I is going to have a value of 3 plus 2 is 5 plus 4, so I should be 9, all right? And J should be 3 plus 5 is 8 plus 10 is 18, all right? So we've added an I of 9 and a J of 18, but D now looks best because remember it was 5 plus 3 or 8. So we choose C, and now we go to, we had chosen C, so the next up we choose D, all right? So we've closed A and C, we're now on D, and we look at D's kids, right? K, L, and M, and we add them in. We see that K is infinity because its H is infinity. L was a 10, right? And M is also infinity. So the J, sorry, I said, so the L, like I said, is 10, okay? Y is L 10, 5 plus 2 plus that is, it cost me 7 to get here, and there are, I think it'll be 3 more to reach the goal. Okay, so I've now closed A, C, and D, and the next cheapest child is I, right? So I choose that, and all it adds is T, but T is infinite, so that's not going to be any good. So I've now done A, C, D, and I, and the next cheapest one we choose is L, all right? And from L, that will get us to W, which appears to have a cost of 9. That's lower than all the other ones, so W is chosen, and that is our goal. The path that we return is ADLW at a cost of 9. Any questions about that? Closed means that we've looked at all of its children. So there's sort of two things. When you first touch a node and compute its heuristic function, we say we've opened it, we've touched it, but we haven't explored its children. The closed nodes are nodes that we've explored the children of. If F prime is predetermined, where does it come from? F prime is simply two things. It's the cost of getting to a node, which you can compute. The numbers that I have on those little arcs, Tyler, are the cost that it takes me to go down that node. Again, remember, think of going from Ruston to Alexandria or Monroe or Shreveport, and in that case, those would be distances. That's information that you know, okay? So the G values are how much it costs to get to a particular node. The H prime values are an estimate of how close I think I am to the goal. And that's probably what you're asking there is, where do those H primes come from? Think about checkers. H prime might be number of pieces that I've captured from my opponent minus the number of pieces my opponent has captured from me. It's some kind of a numerical indication of how good you're doing, okay? Right, you were wondering about H prime, exactly. And Cody is completely right. It is calculated as you go, as you visit the nodes, yes. Okay. But yeah, Tyler was asking about H prime. All right, so what will H prime be? It will depend on the game. H prime generally is some function that in Minimax or in A-star is generally some function that a human has come up with to try to estimate how good a position is. Okay? Now, in more modern AI, right, what we try to do is use machine learning to figure out on its own how good a position is. So that's been kind of what's been happening over the last 10 years or so in gameplay is we still use algorithms like Minimax or Monte Carlo tree search, which is very similar to Minimax, which we're about to talk about, but it tries to get rid of that human knowledge that a human put in there in that heuristic function, because we want the computers to be able to, to learn on their own. Yeah, machine learning is often used together with symbolic AI. And if you look at AlphaGo, AlphaGo 0, Alpha 0, and the new one, Mu0, they all use search spaces and these kind of search trees combined with machine learning. Haley, you don't go through all of the nodes to come up with an H prime. And it doesn't go through the entire graph. And again, look at what I've been saying here. In some ways, showing you guys the whole graph confuses things, right? Because let me just pull off. Let's go back to the first graph we looked at. When you get started, all you know is A. That's all you know. And then you look at the next positions that you can take, the next steps. Well, that's B, C, and E. That's all you know at this point, okay? And then as you go further, you explore more of the graph, but you don't see the whole graph. You're learning it. You're seeing it as you start to explore these positions. So it's kind of like, as I'm trying to show you an overview, I show you the whole graph. You can see it, but the algorithm doesn't see the whole thing. If it saw it, it would just go, oh, this is the path, right? Well, but and normally in the real world, it's not a graph with 10, 12, or 16 nodes in it. It's a graph with millions, tens of millions of nodes, right? So you don't know the whole thing to begin with. That's the whole point. You're searching through the space, okay? Hopefully that makes a little sense. Okay, all right. Any more questions about A-star before we move on to Minimax? And if that's still not clear, Haley, you can talk to me in my office hours. Well, not tomorrow because I'm going to be doing the continuing to do grading, but on Monday. Okay. So let's now move from one-player games to two-player games because that's a lot more fun. And searching a maze is okay, but people really get excited if you build a computer program that can play a human being, right? Then that starts to get fun. That starts to get towards what people think about when they think about AI. The granddaddy algorithm for two-player zero-sum games is called Minimax. And it's been around for my lifetime, and it's an excellent algorithm. These days, it's kind of its cousin, Monte Carlo tree search, which is very similar to Minimax. So you really kind of, just like we needed to do perceptrons before we did modern sigmoid-based neural networks, you really need to do Minimax before you can begin learning about Monte Carlo tree search, because they're very similar in a lot of ways. So what is Minimax? Minimax is a depth-limited, depth-first heuristic search algorithm for two-player zero-sum games. Now, remember when we were talking about blind searches, like breadth-first search, right? or depth first search. We said, well, one idea that you could use is if you can't afford to explore the whole space, you could, go down like 3 moves or 5 moves, and if you go down that far, you just stop and you come back, right? Because I can't afford to look at the whole space, so I just do as deep as I can go. And when I introduced that concept last time, I said, well, yeah, this sounds a little dumb, right? But we'll use this idea in more sophisticated searches. And here's the more sophisticated search, Minimax. Minimax is a depth-limited, depth-first search that uses a heuristic supplied by a human for 2-player zero-sum games. So 2-player zero-sum just means that one of us is going to win and one of us is going to lose. And so if you count a win as a 1 and a loss as a -1, you add up our 2 scores and you come out with 0. So that's what a zero-sum game is. It's a competitive relationship where one person wins and one person loses. So what are some of the assumptions behind the Minimax algorithm, or the characteristics? It assumes that both players want to win. That's an assumption. You ever watch a parent play a game with their little kid? Many times the parent doesn't want to win, right? They want their child to win, and they adjust their level of skill when they're playing tic-tac-toe so that, the child has a chance of winning, right? So it's no fun to always play against someone who's better than you. So it's not always the case that humans always want to win the game. But most of the time when we play a game, we want to win. So that's what the assumption is both players want to win. What's good for one player is bad for the other player. That's another assumption built into it. That's basically saying this is a zero-sum game. What's good for me is bad for you, and vice versa. The last characteristic or assumption in Minimax is an assumption that is clearly wrong. It assumes that the 2 players think exactly alike. And that is not a realistic assumption, but that's the best we can do because we have to model how both people will play the game, or how both opponents will play. Usually one opponent's the computer and the other opponent's a human, but they could both be computers. I guess they could both be people using the algorithm to decide what to do. Now, we'll look at an example, and in this particular example here, and this is very, very simple, we will move first, we being like the computer. And this first layer will be, we want to win, we are playing, so we want a maximum score. This will be a maximizing level. Our heuristic function, we'll still have a heuristic function, h prime, it's still got a prime on it because it's a heuristic, it's an estimate, it's not an exact. We'll score the value of a state on a scale of -10 to +10, where 10 is a win for us, the computer, the thing that's playing, and a -10 is a win for our opponent, that evil human that we're playing, okay? So we want to win. So we want to maximize the score. Our opponent wants to minimize the score. So we want opposite things from one another. If we rate things on a scale of -10 to +10, what's good for us, the computer, are high positive numbers. What's good for the other guy are low negative numbers. They want the opposite of what we want. So let's start off really simple with a single play, a single move. So again, we're at A, and we have 3 moves to B, C, or D. These could be board moves in a board game or whatever, but there are 3 different options that we can take. And so we look at those options. B, we believe is worth 7. C, we believe is worth 5. D, we believe is worth 6. What should we do? Well, we should choose B because B is the highest one. And I want the highest score I can get. So looking at this, it's obvious. If B has a score of 7, C has a score of 5, and D has a score of 6, which one are you going to take? You're going to take B. So the selected move is B, and the heuristic function for A is 7. It's a 7 out of a 10. It's not a win, but it's the best one of those that I have available. Okay, based on our game heuristic, number of pieces that I've captured minus number of pieces that my opponent's captured from me, for example, if we're thinking about checkers. Okay, so that's the whole deal with just one ply. But usually you want to go at least 2 ply. You want to look at what I'm going to do. And again, these are grayed out here, but this is what we had right from above, B, C, and D. But if we go deeper, if we go 2 ply, we get I make a move and my opponent responds to that move. So that's generally better going an even number of ply deep because the computer makes a move and the human responds. Or you could flip this, the human makes a move and the computer responds. So anyway, how is this going to work? Well, to begin with, I don't know this information here. This is going to come back later, right? And this here in gray actually doesn't exist this time. I'm just showing you what it was back here. When we were just going one level deep, we thought B would be a 7, we thought C would be a 5, and we thought D would be a 6. So if this is all we had to go on, we would move to B, okay? But here, what we do is I play the game of, if I move to B, okay, what are the moves that my opponent has? And my opponent would have 3 moves, E, F, or G. Now I have these colored in what's good for me. So G is a win state for me. E is a win state for my opponent, a loss for me. So a loss for me is a -10. It's as bad as we can get. A win for me is a positive 10. That's as good as we can get. F is somewhere in the middle. It's a 5. So I start out at A. I see that it has 3 children. I do not apply a heuristic here. If I had applied a heuristic, I would have gotten a 7, a 5, and a 6. But I don't apply a heuristic here. I instead go one more level deep. So A, I see, okay, what would B be? Okay, there are 3 chances. Now, what is my opponent going to do? Well, I'm assuming my opponent thinks like I do, and he wants to win, or she wants to win. So this is a minimizing node. It is going to choose to go to E, which is a loss for me, because it doesn't want to help me out. It wants to win, so it wants me to lose, right? So if I'm maximizing, it's minimizing. So what is the smallest value of -10, 5, and 10? Well, -10. So once I explore all of these children, all 3 of them, I choose in a minimizing layer the smallest, which is E, and it becomes the choice, and I back up the value of that to this level B. So now then the value of B becomes -10. I'm not done yet. I've only explored the B level. I still have to go and now explore C. C has 2 children, H and I. H is got a value of 2, and I's got a value of -3. Which one is going to be returned? Well, again, they want, this is the opponent is playing. They want me to lose, So they're going to choose a -3, right? So if I move to C, my opponent is going to move to I, and I'll end up with -3. Just like if I had chosen B, my opponent would have chosen E, and I would have lost the game. So at this point, I've explored all of A's children and found out that, from my point of view, the worst of them, from my opponent's point of view, the best for them is E, which has got a -10. When I explored C, same thing, found out I was the worst for me, best for him, so it's a -3. I now have to go and explore D's children, -8 and 3. It's going to take the J to -3. Sorry, it's going to take the J, the -8, and so that's the heuristic value that's returned. So once I do a depth-limited, depth-first search of this entire tree, only going to apply using the heuristic in the final level and back up all of those values, only at that point can A make its choice. And who is A going to choose? Well, I'm still going to choose the best one for me. I've got the choices of -10, -3, and -8. They all look crappy, but C is the least crappy. So I will choose to go to C based on the options that my opponent has to make. And then we would move to C. That would actually be what happens. And then our opponent would move in the real world, and we would probably be at I. That's at least what I predict we would be at. We may be somewhere else because my opponent may not have they may not see things the same way. They may have gone to H. Could have. But wherever we are next time, we'll start at whatever node we're really in, and we'll redo this thing. We'll run a Minimax. We will do a depth first, depth limited search. We're going to go as deep as we can afford. In this case, we can only afford 2. Okay. And when we reach the bottom level, we apply a heuristic and we back those values up. And once we're back up to the current node and we've got heuristic values that have been returned from the lower levels of the search, we make our maximization choice. Okay? At each level, the graph alternates between our turn and our opponent's turn. That is completely correct, yes. Other questions? Okay. Other questions? So that's Minimax. Notice by going one level, one ply deeper, the decision the algorithm made concerning the node to be selected changed. When I only had, I frequently have a hard time grabbing the scroll bar. When I only had one ply, if I only go one ply deep, I apply my heuristic, all right? Because you apply your heuristic at the lowest level. So in this case, I would have gone to B if I only am looking ahead one move, right, and applying my heuristic function. That would have been really, really bad because I would have lost the game, assuming my opponent has any kind of common sense, because he would have moved to E and I would have lost the game. Now, again, I'm making up these heuristic functions, but why might the heuristic function have thought that this was the best move, giving it a 7? Well, because maybe it saw that there was the possibility of winning just one move after B. And that is true. There is the possibility of moving just one move after B. But there's also the possibility of losing, and I'm not in control at this level. It's my opponent's in control. So I want to maximize, but my opponent wants to minimize. And so in the end, while it looked promising when you only had one level, maybe because this heuristic somehow saw that a goal was nearby, right? In reality, there is death awaiting you if you choose B. So by going a little deeper before we applied the heuristics, we saw, no, it's not good. Don't go to B. That'll kill you. Let's try C instead. It's the most promising of what we can see. Does that make sense? Questions? Questions? Y'all are very, very quiet. And I go through all of the details here on this page as to what exactly is happening there that I've talked through. Now, that's the algorithm in a nutshell. You're just swapping between minimizations and maximizations. Now, one of the things is sometimes if you're bright, you can figure out that you don't need to search every node. What do I mean by that? We're going to go 2 levels deep, and you're only going to apply the heuristic at the bottom level. So we're definitely going to have to go and look at all 3 of these children here, right? And we minimize, so we chose E with a -10. So I know A is a maximizing level, so I know that the worst I can do is lose the game. I can get a -10 after I've looked at this. But then when I've explored this level here, this was a 2 and this was a -3, so my mean opponent chose the -3, chose the I. So before I look at D's children, I know that I will do no worse than -3. Before I look at D's children, I know from what floated back up through C that the worst that I'll do is a -3. After I finished with B, before I got to C, the worst that I could do is a -10, lose the game. But after looking at C, the worst my opponent can do to me is give me a -3 if I choose C. So if I have a choice between B or C, I would choose C. Okay? So I know before I even look at D, before I get any information about D or its children, I know the worst I'll do is a -3. Do you agree with that? I'd like to see some feedback in the chat. Okay. Once I've looked at B and C, I know the worst that I'll do is a -3. Okay. Now, when I start on D and I look at its children, the first child I look at is a -8. I am not in control at this level. This is a minimizing level. I want to maximize, but my opponent wants to minimize my chances of winning. So the opponent is not going to choose anything higher than -8 because its first value I found here was a -8. Now, it might choose something, it might not choose J because K might be a -10, in which case D would choose the -10, would choose the K, right? But what if the K is bigger than -8? Well, then it'll still stick with the -8. Values, no matter what the value of K is, D is never going to return anything bigger than -8 at this point. It might return a -9, it might return a -10 if K was a -9 or a -10. So it could go lower than -8, but it will never go higher than -8 because it's already found that J is a -8 and it wants to get the lowest number it can out of all of its choices. Does that make sense? Everybody say yes, that makes sense. D is never going to, once you've looked at J, D is never going to give you anything more than a -8. Might give you lower, it might give you -9, it might give you -10. It's not going to give you anything bigger than a -8. Because we know, okay, that our opponent's in control here, but we're in control here, at this grandparent level, we know that we will never select D after J shows up with a -8. And the reason because of that is that D can be no better for us than a -8. Because that -8 is smaller than the -3 that we've already got, we don't need to ever even look at K. We don't need to evaluate it because it doesn't matter one hill of beans what this value is. Because we will never choose D because we found a value here that was smaller than the value here. And this guy is a minimizing node. It's a minimizing level. And that is called an alpha cut. An alpha cut, okay? And so you might say, well, okay, that's a lot of thinking for one friggin' node, Mike. But remember, we don't normally just go down 2 levels. We might go down 6 levels or 8 levels. There might be a whole friggin' tree down here that we would need to explore, okay? And we can cut off the whole thing because it doesn't matter what K is. It absolutely doesn't matter. We will never choose D once we found out that J was -8. So if J is anything smaller than the -3 that we got here, sorry, you're not going to explore it. That is the basic idea behind Minimax. So Minimax, as I said, can be proved with what's called alpha-beta pruning. Alpha-beta pruning is a way of cutting off search of a particular branch without any possibility of changing the final choice of the algorithm. So it won't change anything. It's just a way of identifying from what I already know about the problem. I don't need to explore this particular path any further because it's never going to be selected. That is the idea behind alpha-beta pruning. And I worked through this. I just verbally described that. So let's look. So let's look at an example here of alpha-beta pruning. Remember, there can be a full tree here, right? Minimax is a depth-first search, so I'm just showing the search down 4 levels of just like the leftmost branch of the tree here. So alpha is a lower bound on a maximizing node that cuts off a minimization search of its grandchildren. That sounds like a lot of gobbledygook, but hold with me for a minute here. So we start off at A, that's the top. Well, what's the worst we can do? -infinity. We have no idea of how bad we can do. So the worst we can do is -infinity. And I'm going to maximize here, and the first node I find is a B. I would have other children that I would look at later. B, this is a minimizing node. My opponent's in control, and it'll have some children. It's first that it finds a C, so you go down there. Now I'm at a maximizing node level again. There'd be a bunch of children. D is the first one. And then I'm at a minimizing level with D. I explore its children, and I get E, and there would be a number of children here. I'm only going to go 4 levels deep. So when I've depth first search as far as I'm going to go, I then apply the heuristic function. So you only apply heuristic functions at the frontier of where you choose to search to. In a sense, the heuristic is a substitute for additional search. I can't afford to really look any further, blindly look using real search. So I just say, I can't afford to search any deeper because my search cost is increasing exponentially. So let me use this heuristic that I've come up with that I think gives me an indication of how good this state is, how close it is to the goal. So when I do that, I find a 2. That E is worth a 2. Okay. I then have to look at all of D's other children. It's got an F that's worth a 3. It's got a G that's worth a 1. Okay. So what is D going to do? Well, it's a minimizing level because remember it's max, min, it alternates. So this is a minimizing level. So what is D going to do? Well, D is going to choose G, which has a value of 1. Okay. When you do that, when you choose the minimum value at this level, right, what happens is the value that you got becomes the floor for your grandparent. C, which is a maximizing node, will do no worse than a 1 at this point. I know that. Okay. So now I've gone all the way down here and I'm back up at C. I look at C's next child, which is H, right? And then I don't apply a heuristic function. I go down the level. I look at H's children. H's first child is a -3. That -3 is less than the alpha floor of 1 that it inherited from its grandparent. Because of that, I know that H, because it's minimizing, will be no higher than a -3. At that point, I can cut, I can alpha prune any other children that H might have because I'm not going to choose H once I know that I is 3 because my mean opponent is going to try to minimize my score and give me no more than a -3. Okay? And that is an alpha cut. And as someone says, as Jonathan says, that is what Deep Blue used to beat Kasparov. That is absolutely correct. Minimax with alpha beta pruning is what allowed the first computer to beat the best human chess champion in 1997. And Eric is also right. It had some book opening moves and some other things and a really good heuristic function. So what are the rules? There are 2 things that can happen. You can either update alpha values or you can do an alpha prune. And the rule is when all of the children, in this case E, F, G, of a minimizing node, in this case D, possess H prime values that are above, all of them are above, the alpha value inherited from the children's grandparent, in this case C is the grandparent, then the alpha values passed back to that grandparent C will be the updated minimum H value for its grandchildren. So that's just putting into words, written words, into a little algorithmic form what I did here. My grandparent had a -infinity, right? Its children, its grandchildren, the children of node D were EFG. D is a minimizing node. The H value of all of those children, 2, 3, 1, are above the alpha value of -infinity. When that is occurring, when all of them are above the grandparent's alpha floor, you take the lowest child in a minimizing node, it's a 1, and that will become your grandparent's floor. That will become your grandparent's alpha cutoff. So that's one thing that can happen. You can update an alpha value. Another thing that can happen is you can prune. When do you prune? You prune when you encounter a child, in this case I, of a minimizing node, in this case H, where the child, I, possesses an H value that is below the alpha cutoff. If they're all above the alpha cutoff, you take the smallest one and you update the alpha. If you find one that's below the alpha cutoff, then you alpha prune. So you're going to either be moving up your lower threshold or cutting off branches that you don't need to explore. You're going to be doing one or the other of those things. The flip side of this is the beta cutoff. So beta is an upper bound on a minimizing node that cuts off maximization search of its grandchildren. So it's exactly the opposite. Okay. So basically, what alpha's doing is alpha's cutting off search at a minimization level. Beta will cut off search at a maximization level. So it's the opposite. Okay. And if we look here, same problem. A, B, C, D, still the same sort of thing. But now we're going to talk about betas, right? Betas are upper bounds essentially, and this is just a summarization of what I gave above. The D is still 1, the H is still less than or minus 3. So these are exactly the same. I'm just not drawing the stuff below. I'm just not drawing this level. It's the same graph that we just had here. Okay. But now let's say D's got a 1 and H has a minus 3, right? So now we're going to explore, well, what happens at the maximization level here? So if we've explored all of C's children, we then go back up to B and we need to explore B's children. Well, let's say B has a J, right? And J has its first child as a K. So now again, we're at a minimization level, 5, 10, 8. So, and the alpha value here is minus infinity. So you take the smallest of these, which is 5, right? All of them are better than minus infinity. So your alpha value gets updated to 5 because that's as bad as things can get for the J here, okay? But now that means that K will have at least a 5, okay? Because this is a maximization level, well, because at the grandparent level, it's a minimization level, and we already got a 1 here, a 5 returned here is never going to be taken because I'm minimizing here, so I'll take a 1 over a 5 at a minimization level. So that means at the maximization level here, where I'm maxing, I don't need to look at these values because J will be worth at least 5. It may be worth more than 5 depending on what's here, but it doesn't matter that it might be worth more than 5. B level is minimizing, so it's going to take the C because it's going to take the 1 rather than the 5. So as soon as you know that K is a 5, you don't need to look any further because you can prune these because at the next level, J is not going to be selected, okay? So that's a beta cut. What we're going to do next time, I didn't get quite as far as I wanted to. We'll look through these again in detail, and then we'll look at a video that will hopefully clear things up, and that video actually has the code in there. So next time, what we're going to do is on Tuesday, I'll finish up alpha beta pruning. I'll show you a video that actually has a pseudocode. It's about a 12-minute video. It walks through, it does a really good job. The code is actually pretty simple. Getting your mind around the concept The concept is pretty simple too, but because things flip back and forth, it can get to be kind of hard to keep it all straight in your head. But you'll need to be able to do that, because I'll give you a graph on the final and say what gets pruned, and you'll need to be able to do that. So we'll go over, we'll finish up Minimax with alpha beta pruning. I'll hand out the programming assignment. I'll hand it out and we'll go over the programming assignment for your last program, because we're pretty much there now. Minimax with alpha beta pruning is the heart of it. Just like just like stochastic gradient descent with backpropagation was the heart of the last program, Minimax with alpha beta pruning is the heart of the next program. We'll do that, and then that's not going to take up the whole class, so then we'll probably talk about Monte Carlo search trees next time as well. Are there any questions at this point? I will have a good weekend. I hope you guys, now that the programming assignment is behind you, will have a good weekend. I had thought about giving out the next programming assignment, making it available today, and then I said, you're not that evil, Mike. We will give them a weekend so that they can chill and relax. Okay. All righty. I will see you guys on Tuesday, and have a good weekend. Take care. Bye-bye.
Thank you.